As you can see from the title, the keyword for the presentation is Lightwave fabrics. So start with a quick overview. So Lightwave fabrics are fabrics that provide direct optical connections or circuits between network endpoints. The key components are an optical circuit switch, WDM optical transceivers that are co-designed with the OCS and the corresponding control plane. The benefits of a Lightwave fabric are they're reconfigurable and can be used both for the data center network and ML use cases. They enable superior performance while maintaining cost and energy efficiency. What will be presented in this talk today is our decade-long experience in engineering these fabrics and specific system-level benefits. First, the Lightwave fabric for DCN. On the left, we have a traditional close-style DCN presented in 2015. On the right, we have the Lightwave fabric-enabled DCN, where the spine switches are replaced with OCSs for a direct connect style topology. By removing the spine, you're removing all the EPS and optics associated with the spine, which leads to very large reductions in CapEx and power. On top of that, you get various benefits such as expansion, so you can bring in additional aggregation blocks later as you need them, connect to the fabric, and restripe with the OCS, so you're paying as you grow. Also, topology engineering, where you're changing the connectivity through the OCS to fit the traffic demand. And lastly, you can mix and match different speed generations of aggregation blocks for heterogeneous networking. Next, we have the Lightwave fabric for our machine learning systems. So at the bottom, you have the fundamental building blocks, which are 4x4x4 3D torus style cubes. So each contains 64 TPUs. These 64 blocks are then attached to the Lightwave fabric, such that any face of the cube can be attached to any other opposite face of another cube. This provides a tremendous amount of flexibility, as you can imagine, allowing different configurations or slice shapes. So as an example, you can adopt the Rubik's Cube shape shown at the bottom, or by switching the OCS and the Lightwave fabric, a cigar shape. This flexibility provides improvements on a large number of parameters, which I'll get to later in the talk. More details of the hardware building blocks. So for our OCS, we chose to adopt a MEMS mirror-based switching approach, shown here. So you have N inputs and N outputs, and by turning the mirror, you can go from one output to another. It's a non-blocking switch with any-to-any connectivity, and you have near-perfect isolation. So a set of connections can be fixed or isolated while changing the other connections. Next, key components are the WDM transceivers and the circulators. So this illustrates the entire link path for the ML use case. So over to the right, you have the TPU motherboard with the TPU ASIC, which connects to the OSFP pluggable optical module. The optical module is WDM, so you're using wavelength division multiplexing, which means you have multiple wavelength channels on a single fiber and OCS port. Now, in addition, we use circulators here, which is a non-reciprocal optical device allowing bidirectional communication on a single fiber and OCS port. This allows an increase in the OCS radix by a factor of 2, as well as a reduction in the fiber count, which we like. The additional benefits of this approach are the OCS and the fiber are, in general, data rate agnostic. So you can use the same hardware over multiple generations of interconnect. The challenges are you have more components, more stuff through this optical path. So that means more optical loss. And with bi-die communication, we have what we call MPI, or multi-path interference impairments. More details of the hardware. So this shows the high-level design of our OCS. The green line shows the optical signal path. So you've got a large number of fibers that are formed into a large array. They're collimated with a lens array and sent out into free space. It hits 2 sets of MEMS mirrors and goes out the other side. Now for the mirror control, we use an 8 to 50 nanometer light source which illuminates the mirrors, and the position of the mirrors is tracked with a single camera image capturing the reflected light. So versus having per mirror monitoring approach, this significantly simplifies the design and the manufacturing. And it's one of the main reasons we chose this design. In terms of performance of the OCS, so I mentioned loss. So we have very low, as well as tight distributions in the insertion loss. Another just as critical parameter is the return loss. It's critical because with a bidirectional link, any kind of reflection along the link path can become noise as it superposes on top of the signal. As you can see for our OCS, it achieves 46 dB typical return loss values. At scale, maintaining this type of performance is quite a challenge. Next, the WDM transceivers. So this shows 5 generations of WDM transceivers, which are developed for the DCN application. Now, what I'd like to emphasize is that these are not standard transceivers, but they're customized for our Lightwave fabric use case. Also, because we're always the lead user, when we want the 200 gig, 400 gig, 800 gig interconnect, there is no existing standard. So we've really had to define the technology ourselves along with our partners. In terms of the design, customization, or optimization of the transceivers, so in order to support higher losses, we've adopted higher speed, higher extinction ratio components. We've also adopted more optical integration. So example for the circulator, it's integrated into the transceiver to reduce the losses. We've also introduced unique forward error correction techniques, as well as digital algorithms, which are embedded inside this DSP ASIC, and going beyond the standards and further increase the link budget. And finally, for the DCN use case, we supported backward compatibility in order to enable the heterogeneous networking, which I mentioned earlier. In addition to further optimize for machine learning, we've adjusted the wavelength plan for the transceivers. So for the DCN optics shown here, we need to maintain a 20 nanometer grid to be backward compatible. In the case of machine learning, the backward compatible constraint is removed. So in order to reduce the total number of OCSs in the system, we actually bundle more wavelengths per fiber. Fewer OCSs means higher availability of the entire system, which is critical for machine learning. What this is showing, so this is a comparison of a system with the Lightwave fabric, without the Lightwave fabric. So if you had our 4,000 plus TPU system and you wanted 97% availability of the slice size shown on the x-axis here, the y-axis shows what percentage of the TPUs you could effectively use versus the remaining to 100% is needed for spares to guarantee that availability. Now, with the flexibility of the Lightwave fabric, you can see larger slices can be guaranteed with reasonable sparing. So you're just picking out the blocks that are working from the entire pool available. Now, versus with a static system in the dashed lines, you cannot. So the bottom line is what it means is you can reliably build these larger slice size systems versus in a static system, you can't. Now, beyond superior availability and efficiency, which I just talked about, here we're comparing model training, which takes advantage of the Lightwave fabric reconfigurability. So the baseline shape is the Rubik's Cube that I talked about earlier. And for LLM2, the optimum shape is the Rubik's Cube. So you get no performance benefit. But for the other LLMs, that isn't the optimal shape. So by adjusting the slice shape with the Lightwave fabric, you can get significant speed up in your training, up to a factor of 3.3x. On top of those availability benefits, here we show a comparison in terms of cost and power. So to the right is a static system as the baseline. Our Lightwave fabric is 6% more expensive and 1% more power, with all the scale, availability, and performance benefits that I just mentioned. Now, you could do an implementation with an EPS-based approach, but you end up with much higher power as well as cost. Now, the additional advantages of the Lightwave fabric versus the EPS solution are you have the job isolation, which I talked about, as well as lower latency. And I'll just throw up the summary slide while we do the Q&A. Thank you.